Okay. What has happened so far? We have talked about sequences, about the problem of convergence, about divergence, about bounded sequences, about many different behaviors that we can see from sequences. Okay? One of the very important class of sequences that we can be sure that they are always going to have some value, that we are going to converge to them, is the class of bounded and monotone sequences. Okay? We have talked about this part. Let me first write this. This is actually a special case of Bolzano-Weierstrass theorem, and I will state it. Any monotone and bounded sequence is convergent. We can also state this theorem in much more general sense, which states like this. First of all, we have talked about subsequences, and we have said that, for instance, this sequence of -1 to the power of n. Sometimes you can select these n's as even numbers, and sometimes as odd numbers, or you can select many different numbers, and these things that you select are going to make a subsequence out of this original sequence. So initially, if you have initially this sequence, for instance A1, A2, A3, A4, and so on, okay? If you drop some of these elements, okay, and construct a new sequence. For instance, I'm just going to select A2, then I'm going to select A3, then I'm selecting A6, then I'm selecting A10, and so on, okay? I'm just selecting some of them and dropping the rest of them. This is called the subsequence of the sequence, okay? Or we can also write this in Nexus in terms of, this is going to be N1, this is going to be N2, this is going to be N3, okay? And if this N1, N2, N3, Nk is an increasing sequence of natural numbers, such that instead of selecting all of these natural numbers, we select only the specific one of them, we are some kind of subtracting subsequences from our original sequence. The general statement of Bolzano-Weierstrass theorem says that if you have a real sequence, and if it is bounded, you can always find a subsequence which is convergent to some point. Okay? This does not guarantee that the sequence itself is going to be convergent. In order to be able to say that, we need something a little bit more powerful, such that being monotone, we will just come to that point. But the thing is that whenever we have a bounded sequence, we can always subtract a subsequence from it such that it is a convergent subsequence. For instance, when we have this -1 to the power of n, okay? One of the possible subsequences here is that we select this n's as 2k, okay? Or we are just only selecting the even numbers. Then what is the sequence? This sequence is going to be equal to 1, which is a convergent sequence or a divergent one? It is a convergent one, and it is going to converge to 1. What about if we select this subsequence? The subsequence such that it is obtained by getting this, an odd number. K minus 1 for natural numbers k. So what is this going to be equal to? -1, and this is going to be a constant sequence, and it is going to be convergent to -1. Okay? Now, if from a sequence which we know that it is not convergent, we can subtract subsequences such that they are going to converge to different points. We can also state that this sequence is not going to be convergent because some of the points of this sequence is going to gather around one point and some other points of this sequence is going to gather around another point. But we know that after some step onwards, all of these elements of the sequences must gather around only a single target value, right? So keep this in mind as well. But the thing is that, and you can prove it as an exercise, if you have a sequence such that all of its subsequences are convergent, and especially this even subsequent and odd subsequence, then we can also say that the sequence itself is a convergent sequence. And we can also say that a sequence is convergent if and only if all of its subsequences are convergent and they are converging to the same root. Okay? This is the case with the subsequences. And the general statements of Bolzano-Irish trust theorem saying that whenever you have a bounded sequence, you can always subtract a convergent subsequence from it. What is important for us here, because we are trying to some kind of understand what kind of sequences are convergent, what kind of them are not convergent. This is giving us a very good criteria. Because first of all, whenever we were saying that 1 over n is going to converge to something, I need to have something. First of all, a target value. Okay, 1 over n is convergent, but convergent to what? It seems that I need to be able to prove two things, or show two things, or claim two things. That first of all, it is going to be convergent and convergent to this target value. Okay? How can we know, without knowing about this target value, that a sequence is convergent or not? This is the cases that we are going to discuss about it. And Weierstrass's theorem here, it is actually helping us to understand if a sequence is convergent or not. Not only that, as you will see in the proof, it is going to be that it is also giving us the target value that this sequence is going to converge to. Okay? This is our claim. Proof. How can we prove this? Without loss of generality. Let's assume that. Let's take this sequence AN and increasing sequence which is bounded from above. What do I mean by this? I mean, first of all, if I have this element of sequence, I have a bound here, such that all of the members of my sequence are going to stay below it. Okay? And since this is an increasing sequence, as I go further and further and further, the elements are going to get bigger and bigger and bigger, or equal to each other. Okay? So, let's take all of these members of the sequence, okay, and put them inside a set. Which means that let's form this. Join us, please. I'm taking this value. This is our real axis, okay? I'm taking this number. All of these, okay? And I'm putting inside a set. It's the set an empty set? It is not empty, right? First, A1 is in that, A2 is in that, A3 is in that. This is not an empty set. Is this a subset of real numbers? Yes, because our sequence is a real sequence. So elements that we are picking are from real numbers. And is the set a bounded set from above? Let me call this set equal to A. Is A bounded from above? Yes. Why it is bounded from above? Because we are assuming that our sequence is bounded from above. Right? So this set A, which contains all of the elements of the sequence, A1, A2, A3, and the rest of them. It is a non-empty subset of real numbers, okay, which is bounded from above. For this kind of sets, what could we say? Remember the completeness axiom? Yes, the least upper bound of the set exists, right? Least upper bound of the set exists. But how can we make use of the least upper bound of this set? By completeness axiom, first of all, by completeness axiom, the least upper bound of A exists. Let's call it alpha, which is the supremum of, or least upper bound of the set A. Okay? If I have a set of upper bounds for this sequence, which means that from here, this is an upper bound, this is an upper bound, and all of these things are upper bounds for it, right? Which one of them is going to be our least upper bound? The one that's smallest of all of them, right? The least of them. And it is some kind of making it come down, such that it is going to touch the thing that they're not going to be able to move farther away from that. Okay? This is this property of least upper bound that we are going to use in order to show that this sequence is actually a convergent sequence. What I'm claiming is this. This sequence AN is going to converge to this least upper bound. How can I prove this? In order to be able to prove this, we need to use a definition. Definitions in mathematics are super important, and we need to always go check them and make use of them in order to prove our claims. Because we are agreeing on the definition, and then we need to make use of it. If I want to show that this AN is going to converge to A, what should I show? I need to show that for any positive epsilon. Okay? We have a natural number which is depending on this epsilon such that for all n, if n is greater than or equal to this step, then an minus alpha is less than epsilon. Okay? What is this claim that I'm making? As you know, I can write this in this form, right? Since absolute value of this is less than epsilon, we can write this as this is greater than minus epsilon, that is here, and less than epsilon. So we have this minus epsilon, an plus alpha less than epsilon, which I can also write it as, taking this epsilon here and here, I can write it as alpha plus epsilon, alpha minus epsilon. Okay? So what we need to show, what we need to prove is this. if I have this increasing sequence, which is bounded from above, okay, and this is going to be my least upper bound, I'm just going to claim that this sequence is going to converge to this number. And in order to be able to show that, I need to take an error bound, epsilon, and I need to show that if I have a narrow band around this, okay, after some step onward, all of these elements of the sequence are going to get inside of this. First of all, this part is very obvious. Why? When I say that no matter what my n is, elements of the sequence are always going to be smaller than alpha plus this epsilon that we have. What was our alpha? It was our upper bound, right? Since it is our upper bound, all of the elements of our sequence are smaller than that. Since alpha is an upper bound, ANs are less than equal to alpha. And if we add some positive number to it, it is going to be like this, right? So this part is true. This part, you can easily show that. But what about this part? How can we show that if from this target of least upper bound, if we come a little bit down, okay, or to the left or whatsoever, as the way that you want to think about it. After some step onwards, we are always going to have all of the elements of the sequence AN stay above that. How can we claim this? How can we show it? Any ideas? Yes, it is increasing monotone. Yes. Yeah. This is actually the thing that we are going to say. Look at this. You have the sequence, which is an increasing sequence, right? And alpha is the least upper bound of it. Among all of the upper bounds, it is the smallest of them. If we have no element of AN such that it is bigger than alpha minus epsilon. Or in other terms, if all of our elements of the sequence are going to be smaller than equal to alpha minus epsilon, then what will happen? Alpha minus epsilon will be an upper bound, right? And it is going to be that upper bound which is less than the least upper bound. And this is some kind of contradiction with the definition of least upper bound, right? Because among all of these upper bounds, we are selecting the smallest one of them as our alpha. This is the supreme or the least of them. If we can say that we can decrease this to alpha minus epsilon, and none of these elements are above that, then alpha minus epsilon is an upper bound, and it is smaller than alpha. Since alpha is the least or the smallest of upper bounds, there is a natural number, let's call it this n, capital N. There is an n such that what I'm claiming is this. Since alpha is the least upper bound, if I come a little bit below it, I must find an element of that sequence which is greater than that. Because if I'm not able to find it, then all of these elements of our sequence are below alpha minus epsilon, which means that alpha minus epsilon is the upper bound which is smaller than the least upper bound, which is a contradiction. Okay? Now, if this happens, let's take this capital N and look for all n's that are bigger than that. Now, for n greater than equal to this n, we have this sequence was an increasing sequence, right? Which means that if I proceed further, if I pass this step and increase, the values of my sequence are also going to be increasing, or it is going to be something like this. Okay? Look at this. At this step, I'm able to find something which is above alpha minus epsilon. And since my sequence is increasing, all of them will also going to be above that. Which means that alpha n's, ANs, are going to be above alpha minus epsilon for this. So what is happening? How I've been able to show this part as well? Yes, we have found a step such that after that step onwards, all of the elements of our sequence are going to be staying above this. Which means that we have both shown this part and this part, which proves our claim. Okay? Which means that this is going to be a convergent sequence. And to which value this is converging? The supremum of that set. Okay? We can also make another thing, which is we can say about decreasing sequences. Okay, decreasing sequences. If we have a decreasing sequence which is bounded from below, then that sequence we can be sure that it is going to be convergent. And not only it is going to be convergent, we can also say to which value it is going to be convergent. It is going to be convergent to, among all of these least upper bounds, among all of these lower bounds, it is going to be converging to the greatest of them, yes, biggest one. Okay, for instance, look at 1 over n. Take 1 over n, this sequence. Okay? Is this a decreasing sequence? Again, if you have it, this is 1 over 2, 1 over 3. This is a decreasing sequence, right?
Yes.
Is it bounded from below? Yes. What is the set of lower bounds of this sequence? Is this number, for instance, -1 a lower bound? Yes. -2, minus whatever. All of these negative numbers, they are all lower bounds for this, right? What is the greatest of them? 0, right? Yes, but x-axis here, this is our real axis, okay? And we're taking the values of our sequence from here. So we need to look at this. Among here, if this is 1, if this is 1 over 2, if this is 1 over 3, 1 over 4, and so on, the things that we need to project it here, okay? What is the greatest of lower bounds? 0. Again, by this theorem, it is going to be converging to 0. And we have been able to prove this without referring to this theorem, right? So this is one of the theorems that we can have as a tool in order to be sure that the sequence is going to be convergent, okay? There's also another subject that is important for us. Another concept which is important for us is the concept of Cauchy sequences. We are going to call a sequence a Cauchy sequence. Then, after some step onwards, the distance between elements of the sequence are going to get closer and closer and closer to each other. Which we can state that AN is a Cauchy sequence if any positive error bound, there is a natural number which is depending on this epsilon such that for O, N, and M, if N is greater than this step, M is greater than this step, then distance of AN from AM are getting less than epsilon. What does this mean? Let's look at the convergence sequence. For instance, this sequence. Okay? I'm some kind of trying to write -1 to the power of n divided by n. Okay? If we select an error bound of epsilon, a positive real number, can be anything. we can say that after some step onwards, the distance between these elements, are getting smaller and smaller and smaller. If this kind of a thing happens for a sequence, we call that sequence a Cauchy sequence. Okay? You can show that. I'm just going to leave this to you, that any convergent sequence is Cauchy sequence. Why? Can we intuitively think about this? If we have a convergent sequence, what will happen? We will have a target value. After some step, all of the elements of this sequence are going to gather around that target point, right? And they're getting closer and closer to that target value. If they are all gathering around that target value, can we say that they're also getting closer and closer and closer to each other? This is exactly the statement that's here. But you need to write it down to have it exactly. One other claim is that all Cauchy sequences are bounded. So whenever we are having an unbounded sequence, it is not a Cauchy sequence. For instance, the sequence N is not a Cauchy sequence because it's not a bounded sequence. But why? Cauchy. Convergent mi?
Bound olduğu için bound olanlarda
Bounded, her bounded olan sekans, Cauchy sekans mıdır? Can we say that any bounded sequence is a Cauchy sequence? Let's again think about this -1 to the power of n. Okay? This is a bounded sequence, right? But is it a Cauchy sequence or not? If it was going to be a Cauchy sequence, after some step, the distance between elements of the sequence needed to be get closer and closer and closer as we desire. But they're jumping from 1 to -1, 1 to -1, and it seems that they are having this distance of 2 between them, which we cannot get them closer to each other. Which means that it is not a Cauchy sequence, but it is a bounded sequence. This way is true. If we have a Cauchy sequence, yes, it is a bounded sequence. But what about the inverse? What about if we have a bounded sequence? Can we say that any bounded sequence is a Cauchy sequence?
No.
No, we cannot say it. But again, question, why any Cauchy sequence is a bounded sequence? How can we argue about this? If I have a Cauchy sequence, all of the elements are going to gather around each other. And since they are going to gather around each other, we can also say that they are staying below something or above something. They're close to each other. We don't know if they are close to a real number or anything. We don't know if they are close to a target. But we know that they're close to each other. That's why we can say that yes, we can bound them actually. One beauty of real numbers is this. If you remember how we constructed a set of real numbers, you're constructing Dedekind cuts, and we were some kind of trying to fill that gaps, right? There is also another way that we can reconstruct the set of real numbers. And it is that we are taking all of the Cauchy sequences which are coming or which are Cauchy sequences on the set of rational numbers. And we some kind of define an equivalence relationship between them. And each equivalence relationship is going to be a real number. What I mean is this. When we are dealing with Cauchy sequences, they are gathering around. They're gathering elements of that Cauchy sequence, they're gathering around. If there is a gap or no gap, it doesn't matter for them. They're all going to gather around something. When we are constructing a set of real numbers, if these Cauchy sequences are gathered around rational numbers, we call that rational number, yes, the equalence class of that Cauchy sequences. If the elements of Cauchy sequence gather around an empty spot, a gap, then we are saying that, okay, you see this gap that these Cauchy sequences are going to gather around it. This is going to be a real number. And all of those gaps are identified by the equivalence class of Cauchy sequences. So this is something, a side note, but keep that in mind that the Cauchy sequences are also useful in the construction of real numbers. But what is important for us? What is important for us is this statement. I'm just going to state it and get out with it. In R, even in n-dimensional Euclidean spaces, any Cauchy sequence is convergent. And any space such that in them Cauchy sequences are convergent are called a complete space. The name of the completeness axiom and so on is also coming from here. Because in the set of real numbers, whenever we are having a Cauchy sequence, it is going to be a convergence sequence. Okay? Why Cauchy sequences are important for us? Because in the set of real numbers, if I have a sequence, and if I know that it is a Cauchy sequence, without knowing the target value, only by knowing that their distances are going to get closer and closer to each other, we can be sure that they are going to be convergent. So far, we have been using the definition of the limit, and also we have been looking for the conditions that we can be sure that sequences are convergent or not. But the thing is that, how can we really work with this kind of sequences? And if we have some sequences and if we want to find their limits and so on, how can we do this? This is what we are going to do in the rest. What I'm claiming is this. And these are going to be some tools for us to calculate the limits of these kind of sequences. If a sequence AN is going to converge to A, and sequence BN converges to B, then AN plus BN is going to converge to A plus B. For the subtraction of them, this is also true. If I multiply the sequence with a constant, then this sequence is going to be converging to C times that limit. about multiplication of two sequences? If you multiply two sequences AN and BN, and AN is converging to A, BN is converging to B, what is this going to be? Yes, A times B. A times B. What about AN divided by BN?
A.
Yes, A divided by B in the case that A is not equal to 0. Okay? A few examples. What is the limit of 1 minus 1 over n to the power of 2? Tamam, şuna cevap ver o zaman. What we are saying is that we need to take this one and this one. This is AN equal to the constant sequence 1. And we have this sequence Bn 1 divided by n to the power of 2, right? What do you see is this limit of An minus Bn. According to this, we can write this as limit of 1 minus limit of 1 divided by n to the power of 2. When can we do this? If we know that this limit exists, this limit exists. So, does this limit exist? What is the limit of 1? What is the limit of a constant sequence? 1, yes. So this limit exists, which is equal to 1. What about limit of 1 divided by n to the power of 2?
0.
0. Why?
Because limit approaches 0.
It approaches 0. And we have actually proved this for any n to the power of p, n to the power of 1 divided by n to the power of p, which p is a positive number, positive real number. The sequence is going to be converging to 0, so this is like minus 1. Okay? What is the limit of n minus 1 divided by n? Why? Yes. No matter what you claim, and your claim is right actually, the limit is going to be 1. But you need to prove it. Can you prove that your claim that this is going to be 1 is true? Which I mean that what kind of steps you are taking. What we are doing is this. Look at this. We have this sequence divided by this sequence, right? Can I write question? This has limit of this n minus 1 divided by limit of this n. No, actually no. Why yes? Here, look at this. Here we have this. This is limit of an divided by bn equal to limit of an divided by limit of bn. Okay? This is this thing which we are doing here. But when we can do this, when we know that this sequence is convergent, this sequence is convergent. Please don't forget this condition. We have a huge if here. If this is not true, we cannot use these. Okay? One other thing to remember. You need to know under which conditions you can use the tools. If the conditions are true, we can use these tools. If it is not true, then we are not going to be able to, and we should not use these tools. So if you write this like this, what is the limit of n minus 1? Infinity, or some kind, it is divergent, right? It is divergent to positive infinity, and this one like that. Infinity divided by infinity. So we have an indeterminate form, okay? Which is not true. So since this limit doesn't exist, this limit doesn't exist, we cannot say that we can do this. What is the better approach? What is the better approach? It is like this. As you said, we can take this as limit of, take this and separate these two into two expressions like this. Okay? If you do this, what will happen? Can you argue please now? Sıfıra çok yakın olacak demeyi bırakıp da limit hakkında konuşsak nereye gidiyoruz? Can we now again argue like this, that this limit is going to be limit of this sequence minus the limit of this sequence? Because the limit of 1 and the limit of 1 over n, both of them exist, right? So we can separate them. What is the limit of 1? What is limit of 1 divided by n?
0.
So, are we done? Good? Let me talk about something general. Can you find this limit? What? 4 n to the power of 5 plus n3. Does this limit exist or not? Or does the sequence, is the sequence a convergent sequence or not? Yeah.
I think it's exists.
Okay, and if it exists, what is the value of the limit?
Value of limit is 2.
How do you calculate it? Can you please also illuminate us?
Well, so I take n over 5 out of that.
I got your point. If we take directly the limits, this is going to be infinity divided by infinity, which means that we cannot separate this here and here. What we are going to do is this. Here, from n to the power of 5, or with the highest degree term of this polynomial, take that as a factor out. Write this as n to the power of 5, 4 plus n to the power of 3 divided by n to the power of 5. Okay? Again here, from the highest degree term, take a factor out. This is going to be n to the power of 5. 2 plus 1 divided by n to the power of 5. Okay? This n to the power of 5 and n to the power of 5 cancel each other. And what do we have then? Limit of 4 plus 1 divided by n to the power of 2. 2 plus 1 divided by n to the power of 5. Right? Now, does this sequence has a limit? Yes. Does the sequence has a limit? Yes. So I can take this limit to here and here, which means that I need to take the limit of this. Ne yazıyorum? Cancel. How many A's do we have? Two plus 1 divided by n to the power of 5. Okay. What is the limit of this sequence? Again, we can argue that this is going to be limit of this one plus limit of this one. Here we are writing a lot of steps, but we are just going to get rid of them and write them much more simpler. So this is going to be what? 4. What is this limit? 2. And the result is going to be 2. You're done. Okay? Much more general case. When we have a polynomial divided by another polynomial, okay? When you're having this limit of, for instance, ak n to the power of k plus lower degree terms bm n to the power of m plus lower degree terms. Again, we can use the same argument that we had done for this example. Take this exponents out, and this limit is going to behave like limit of ak n to the power of k bm n to the power of n. Okay? Which is going to be, if this exponent is greater than this, if k is greater than n. For instance, when we are looking to limit of 4 n to the power of 4 to n to the power of 2, okay? What will happen? When we cancel these, we are going to have an n in above, right? And is it going to be a bounded sequence or not? It's going to be an unbounded sequence. N to the power of 2, n to the power of 3, or whatsoever. N to the power of a positive integer is an unbounded sequence. So it is going to diverge to positive infinity or negative infinity. Depending on what? Depending on this signs of AK and BM. Okay? If this is going to be a positive number, it's going to be positive times positive infinity, which is going to be positive infinity. If this is going to be a negative number times positive infinity is going to be a negative infinity. Which means that we can write this as sine of AK divided by BM multiplied by this positive infinity. If K is equal to M, what will happen then? This n to the power of K and n to the power of K, they will cancel. This will be the constant sequence, AK divided by BM. And the limit of a constant sequence, you know, that is just that constant, not 1. If this is 1, yes. So it is going to be AK divided by BM. What happens if K is less than M? Which means that we are going to have an M. All of the n's on the denominator are cancelled. We have some additional n's in the denominator. It is going to behave like n 1 divided by n to the power of p, right? And what was the limit of that? 0. This is all the cases. First of them is that sandwich theorem. For 3 sequences, AN, BN, and CN. If after some step we have this BN staying between CN and AN, and if AN is converging to a limit L, CN is also converging to the same limit L, then what can we claim about the limit of Bn? Or what can we say about the convergence of Bn? We need to look at this in this way. If I have this, we can take the limits. So it is going to be limit of An less than equal to limit of Bn less than equal to limit of Cn, okay? What is this limit? Limit of An, as we are assuming, yes, L. What is this limit? Again L. So what is this equal to? So this is also going to converge to the same limit. Okay? Example. What is limit of sine of n divided by n? Or a better question even. Is the sequence sine of n divided by n a convergent sequence or not? And if it is convergent, to which value is it going to converge? How can we use this theorem? Look at the values of sine.
1 and minus 1.
Artırma yine aklında olursun. The sine of n, or sine of x if you take it as a function. The values of sine of x as a function is always between -1 and 1. So instead of x, if I place this natural numbers n, it is also going to be between -1 and 1, which means that we are going to have this, okay? From this, how can we arrive to this one? What are the similarities and differences? Yes, divide by n, right? Divide by n. If I want to come to this, from this, I need to divide all the parts by n. Is it true? Now, take limits of these sides. What is limit of -1 over n?
0.
0. What is limit of 1 over n? So, if this is 0, this is 0, what is the limit of sine of n divided by n? Okay? Fine? We have some cosine squared of n divided by n. Cosine to the power of 2 of n divided by n. What is happening is this. Again, we can say that cosine is between -1 and 1, right? Cosine of n. Cosine is also between -1 and 1, right? So what will happen to cosine squared? If we square these sides, it is going to be staying between 0 and 1. And since I want to have this cosine squared divided by n, again divided by n, if I divide this by n, 0 divided by n, 0. This is what I'm after, and this is going to be 1 divided by n. Right? Now, if you take limits, what will happen? This is 0, this is going to be converged to 0, so this is also being a convergence sequence, and this limit is going to be again 0. If an is a bounded sequence, and if Bn converges to 0. By the way, any sequence that is converging to 0, we normally call it a null sequence. Okay? You have a bounded sequence, you have a null sequence. Then, An times Bn is going to converge to. What we are doing is this. Let's use this definition. If An is bounded, what does it mean? It means that for all of the values of this index, this is going to be less than or equal to a real number, right? Which we can also write it as this. Okay? Now multiply both hand side with Bn. What is this going to be? A number times Bn less than or equal to A and Bn less than or equal to m times Bn.
0.
Now take limits. What is the limit of this sequence?
0.
A constant sequence, its limit is minus m. What is the limit of Bn? 0. So both of this limit exists, so we know that the limit of this exists, and it is equal to 0. What is the limit of this one?
0.
It is also 0. 0, 0. So by the sandwich theorem, it is going to be 0. Okay? So can you please calculate this limit? -1 to the power of n divided by m to the power of 2. What is this limit? Take this An as the sequence, -1 to the power of n. Okay? And Bn as 1 divided by n to the power of 2. Is this a bounded sequence? Is this a null sequence? And if we multiply them, do we have this sequence or not? We have it, right? Since we have it, An times Bn's limit is going to be, according to this, equal to 0. Right? If the function f is defined for x greater than some n, and if we have An defined as values of this function at integers for n greater than or equal to this n, then limit of An as n goes to infinity is equal to L if limit of this function f of x as this x goes to positive infinity is going to be equal to L. What does this mean? This means that if you have a function which is defined after some points on, okay, maybe from here, okay? And I'm looking at the values of this function on natural numbers, okay? For instance, I'm looking at this natural number, I'm selecting this one. Looking at this, selecting this one, looking at this, or what I'm constructing is this sequence, okay? This sequence is going to converge to some point okay? In the discrete sense of jumping from 1, 2, 3, 4, and so on. If this function's limit, as this x a real quantity, converging to positive infinity, converging to this value. Why this is useful for us? Let's look at an example. What is the limit of ln of n divided by n? How can we calculate this? Apparently we do not have any tools to calculate this, right? But look at this, the thing that we have here. If we take this function f of x as ln of x divided by x, this is a function defined for all positive real numbers, right? If here, instead of x, we plug natural numbers, 1, 2, 3, 4, all of those. Is this sequence popping up or not? In this function, instead of x, if we write n, do we have this sequence? Yes. Which means that in a function, instead of x, we are plugging n, and we are acquiring a sequence. Now, in order to calculate this limit, according to this, okay, all of these claims, I'm leaving them for you to prove. According to this claim, what you're going to have is this. I need to only calculate the limit of this function, ln of x divided by x. What is this limit? From calculus 1, you should probably remember it. Let me also draw this graph of ln of x. This was our ln of x, right? If x goes to positive infinity, the value of ln is also blowing up, right? It goes to positive infinity. So this is in the form of positive infinity defined by positive infinity. And this is an indeterminate form. Positive infinity divided by positive infinity is not defined. How to calculate this kind of limits for functions which are defined in the real line? And you know that if we have, for instance, infinity divided by infinity or 0 divided by 0, which is an indeterminate form, we can use L'Hopital's rule in order to find this kind of limits, right? In order to be able to take derivative of something, it must be defined on open subsets, or the things that we can take their limits, right? On the set of natural numbers, the sequence is, for us, it is meaningless to take its derivative. But if it passes to the real numbers, then we can talk about the derivatives and this kind of things. So we have more tools to use. That is what. Look at this first of all. If this limit existed and this limit existed, I could say that, okay, this limit divided by this limit. But when I'm taking limit of ln of x, as x goes to positive infinity, unfortunately, it does not have a limit, and the result is positive infinity. As we go to positive infinity, the values are also going to go to positive infinity. And what about the values of x, or the limit of x at positive infinity? It is also going to be positive infinity. So this limit is an indeterminate form in this version. Okay? So how can we get around this? How can we solve this problem? What we need to calculate is this. Since the limit of ln of x divided by x is infinity divided by infinity form, we can calculate limit of derivative of nominator. What is derivative of ln of x? 1 over x. Derivative of ln of x divided by derivative of denominator, which is going to be limit of, I'm writing this all the time. Derivative of ln of x, as you said, is 1 over x. Derivative of x is 1. So this is going to be limit of 1 over x as x goes to positive infinity. And what was this limit? 0. Since this limit exists, limit of derivative of numerator divided by derivative of denominator, this limit also exists, and the value of this limit is also 0. Okay? Which means that the limit of ln of n divided by n is also equal to 0. Okay? Please also add this limit into our list of limits. 1 over n, 1 divided by n to the power of p, sine of n divided by n, ln of n divided by n. Okay? Good? A function f is continuous at L if and only if and only for all sequences like an such that they converge to L, we have limit of f of an as n goes to positive infinity equal to f of L. What does this mean? Let me write this in this form. Limit of, I'm just keeping this, f of an. What was our L? L is the limit of an, right? Limit of an as n goes to positive infinity. So what happens here? This statement is saying that if you have a continuous function and if you have a converging sequence, we can change this f and limit, or let me state it much more better. If you have a sequence which is converging to some point, and if you have a continuous function, then this limiting process and taking the value of the function, they can be changed. Or in other words, it means that if you have a continuous function at some value, this limit value, then we can put this value inside of the function, this limit, or we can take it out. So continuous functions have this property that the limit and calculating their value can be interchanged. How can we calculate this limit? Or does this sequence square root of n plus 1 divided by n, does it have a limit?
Yes.
Is it convergent? What is that value? How do you calculate it? What you're saying is actually this, right? You're going to take the square root of limit of this n plus 1 divided by n. Why can we write this kind of thing? Why can we push limit inside the square root?
Sure.
It is because of this fact. Why? Is the square root a continuous function?
Yes.
Since it is a continuous function, you can push the limit inside of it. So it is going to be pushed inside. Now we have this. And what is this limit? It is going to be behave like n divided by n, right? Which you can cancel it, and it is going to be limit of 1. And it is going to be square root of 1, which is going to be 1. Okay? What about limit of e to the power of n2 plus 1 to n2 plus 3? What is this limit equal to? What happens is this: if we can calculate this limit, and if we can take this up here, then we are done, right? So question, is the exponential function a continuous function or not? It is a continuous function, right? So we can push the limit inside of it. So this is going to be e to the power of limit of n2 plus 1 to n2 plus 3. Why we can do this? Because exponential function is a continuous function. You can push it inside, okay? Now look at this. How is this going to behave? This is going to be limit of what is the highest degree term of this polynomial? N to the power of 2. What is the highest degree polynomial of this? 2 and 2. You can cancel 2 and 2 and 2 and 2. And we have 1 over 2, right? What is the limit of 1 over 2? So this is going to be e to the power of 1 over 2, which is square root of. We have talked about the limit of real sequences up to now, but we can also extend this to complex numbers as well. If we have a complex sequence, which we can write in this form, an plus I bn, okay? And we say that this complex sequence is going to converge to a plus ib. If and only if, the real part of this sequence is convergent, and it is converging to a, and the imaginary part of the sequence is also convergent, and it is converging to the number b. Okay? And real part and imaginary part of this are real sequences, so we know how to work with them. Okay? For instance, what is the limit of 1 over n to the power of t plus I times ln of n divided by n? What is the limit of this complex sequence? The real part of this sequence is 1 divided by n squared. And it is a convergent sequence. And it is convergent to 0. What about ln of n divided by n? It is also, which is the imaginary part of the sequence, it is also a convergent sequence, and to which value it is convergent? To 0. So this is a convergent sequence, and it is going to be converging to 0 plus I0, which is going to be complex number 0. What is limit of z to the power of n? Z is a complex number. How can we reason about this limit? Let's go case by case. If z is equal to 1, what is this turning into? 1 to the power of n, which is 1. And what is the limit of 1, which is a constant sequence? 1. Limit of z to the power of n is equal to 1. If the absolute value of z, or modulus of z, is equal to 1, what will happen then? Which means that in the complex plane, where we have this unit circle, okay, we are selecting a number here, z, or any place that you want to select. If we have this, what will happen to z to the power of 2? If you remember, we talked about geometric way of multiplicating this complex number, right? Multiplication of complex numbers with some kind of rotating them and multiplying their distance from the origin. If I have this number, which has its distance equal to 1 and angle theta, okay, its argument is equal to theta. If I multiply this to itself, what will happen? It will be 2 theta, and this distance again will be 1, which will be staying on this circle, but this time the angle will be 2 theta. So maybe it's going to come here. If I multiply it again to itself, so what is z to the power of 3? This is z, this is going to be z to the power of 2. It is going to be z to the power of 3 here, okay, with 3 theta. And if you multiply it, what will happen? It's just going to rotate. Is there any complex number such that after some step onwards, these elements are going to accumulate around that point in the complex plane?
No.
What I'm asking is this. If this is going to be a convergent sequence, what should happen? After some step, they must gather around a fixed complex point, right? Definitely it is not going to be here, outside of this, and not inside of this. It must be somewhere in the circle, right? But if it is in the circle, for instance here, and if I look at it's around, okay, it's neighborhood, right? With this metric that you have shown that it's actually a metric with in your exercises. But you have defined for complex numbers. Is it going to be after some point all of these z to the power of n's accumulating around this point or in this circle? Unfortunately, no. It is just going to rotate. It is always going to escape any neighborhood that you're going to get selected. Okay? So it is going to be divergent. What about if we select something that has a modulus less than 1? Which means that if it is inside of this unit circle. For instance, something here. If you multiply this to itself, what will happen to this point? Yes, again it is rotating, but this time, since its modulus is something less than 1, as we multiply it to itself, it is going to get smaller and smaller and smaller. So it is going to be rotate here. And they're going to accumulate around which point? 0. So this limit is going to be limit of z to the power of is going to be 0. What if this absolute value is greater than 1? If, for instance, we select some point outside of this unit circle. Since this distance is going to be bigger than 1, when we are multiplying this thing to itself, although it is going to be rotated, but this time it's going to get farther and farther away, right? So it is going to again diverge. Okay. So one thing that you need to also add to our list of limits. Limit of x to the power of n is equal to 0. Now I'm not using a complex variable, but real x. If absolute value of x is less than 1, x is in R. And if is x greater than 1 or equal to 1, what will happen? If x is equal to 1, we know that it is going to be converging to 1. If it is minus 1, then it is oscillating minus 1 to the power of n. It is not going to be convergent. If it is less than minus 1 and is strictly bigger than 1, then it is going to be divergent because then it is going to be an unbounded sequence. Okay? Question. What is limit of n is root of p if p is a positive number? For instance, what is the limit of n is root of 5? Which means that if we take this sequence 5, square root of 5, third root of 5, fourth root of 5, what will this sequence converge to? Why 0? That's a claim, you need to prove it. Learn something and let's discuss it. What is happening is like this. We can write this as this number p to the power of 1 over n, right? So look at this function. F of x equal to p to the power of x. It is again an exponential function, right? Is this exponential function a continuous function or not? Exponential functions are continuous functions from calculus 1. So what happens here? I can take the limit inside. So I can write this as p to the power of limit of 1 divided by n. Right? And what is this limit equal to? 0. So this is going to be p to the power of 0, which is going to be 1. Okay? Please also add this limit to the list of our limits. Important limit. What about this? Limit of n root of n. What you can tell about this? Look at this. If we define this function, x to the power of 1 over x, or positive x's, okay? And if I plug n here instead of x, am I going to get this one? Yes. So I need to look at the limit of this function. But what is the limit of this function? Again, infinity to the power of 0, which is indeterminate form. So I need to do some kind of change in how I'm behaving with this function. You know that e to the power of x and ln of x, okay? These are inverse functions. Which means that if here, instead of x, I plug ln of x, I'm going to get into the identity function, which is x, and to be able to define ln of x here, x must be a positive number. And we can also, instead of here in ln of x, plug e to the power of x and get this as x. Okay? So look at this. If I have any number x, I can write it as e to the power of ln of x, right? If, for instance, this x was a to the power of b, if it was a to the power of b, how could I use this for this number, if this is my x? It is going to be e to the power of ln of a to the power of b, right? And you know that this exponent in the ln can come as a coefficient here, which is going to be e to the power of b times ln of a. Okay? Now let's look at this. What is my a here? X. What is my b here? 1 over x. So I can take this limit of x to the power of 1 over x as limit of, let me use these things here, as e to the power of, what was our b? 1 over x. What was our a? This is actually ln of x. Okay? Right? So what is this? This is equal to limit of e to the power of ln of x divided by x. How can I calculate this limit? Again, exponential function is a continuous function. We can pass limit inside, which means that this limit comes to the exponent, which is going to be e to the power of limit of ln of x divided by x. What was the limit of ln of x divided by x as x goes to positive infinity? 0. It was 0, right? So this is e to the power of 0, which is 1. Okay? So this limit of n root of n, is also equal to 1. Please also add to our list of limits. I will give you 2 exercises. Show that limit of n going to the positive infinity of x to the power of n divided by n factorial is equal to 0. For any real number. Instead of x, you can write any real number. 2, 5, minus 10, a billion, whatsoever. This limit is always going to become 0. This is also the reason that we say that factorials grow faster than polynomials. Okay? is Euler's constant, or the base of natural logarithm. Show that this sequence, which is defined as 1 plus 1 over n to the power of n, is an increasing sequence. And is bounded from above. And you can say that it is actually bounded from above by 3. Number 3. Okay? Now, question. If this is true, what can we say about this sequence? Is it going to be a convergent sequence or a divergent sequence? We have a sequence which is an increasing sequence and is bounded from above. What will happen to this kind of sequences? It is going to be convergent, right? We have proved this. And it is going to be convergent to which value? The least upper bound of the set of all of these values, or the supremum of that set. Okay? So this limit really exists. And since this limit exists, we give a very special value to it, which is this number e. We define this number e, the Euler's constant, as the limit of this sequence. Okay? We are also going to give another equivalence definition for this number e when we are talking about series.